In this video, we're going to do a walkthrough of an HDFS file write. I really honestly think this is probably one of the most important videos we have in this course. We're going to do a step-by-step write operation, how the client interacts with HDFS to put the file into the system, both through the name node as well as the data node, how blocks are calculated and written, how our replication factor is ensured, as well as how failsafes are handled. First of all, let's introduce the key players. We have a client, which sits outside the cluster. We have the name node, which is our master daemon that does our orchestration and delegation. And we have one or more data nodes, which are the slave daemons that handle the actual data storage. At a high level, the block write includes all of these steps. The client first cuts the input file into chunks of the given block size. The client then contacts the name node to request a write operation. It sends the number of blocks and the replication factor that need to be ensured. The name node then responds back to the client with a pipeline of the data nodes to write the first block to. The client reaches out to the first data node, again that's the slave daemon, in the pipeline, and it performs the write. The client is talking directly to the data node here. No actual data transfer ever flows through the name node. The second and third data nodes all then write data directly to each other. The client only contacts the first data node in the pipeline. After the last data node in the pipeline responds, the client is notified of a successful block write. The client then notifies the name node of the block write, and then the name node responds with the pipeline of data nodes to write the second block to. Then we keep doing these steps over and over for every block in the system until the last block is written and the file is closed in the name node. At this point, the file can no longer be written to. It's what's known as immutable or unchangeable. Now let's actually take a graphical walkthrough of everything we just said there. First of all, let's say that we've got on the client this file, 2013 Apache logs.txt. This is a log file of all of our Apache logs over the year 2013. Let's say it's a 500 megabyte file. Pretty good size. We probably don't want to process this all on one single client. Let's say our block size is set to the recommended 128 megabytes, and our replication factor is set to the default 3. Again, block size is the number of chunks it'll be cut into, and replication factor is the number of times that each one of those chunks will be stored. We put our file up into Hadoop with this command on the client. This uses the Hadoop API, specifically the file system API, to do a put operation of this file into this path in HDFS. Again, the replication factor and the block size all came from the client configuration. They could have also come from the name node configuration, but in most cases, the client will have that loaded locally. The client then cuts our file into 4 blocks. Again, we get 4 blocks by dividing the 500 megabyte file by the individual block size, 128 megabytes. So we get 3 chunks of 128 megabytes, and our last block, block 3, is going to be whatever's left over. The client then sends this put request into the name node. Again, this is initiated from this Hadoop FS command. The client is telling the name node that we need to put this block 00, the upper left half of this file in this case, into the name node. Again, these 4 chunks of the file are just to make it visually clear that our file is broken into 4 pieces. Actually, what happens is the first 128 megabytes of the file exists in this block 000. The name node then sends back to the client what's known as a write pipeline. In this case, it's going to consist of 3 individual data nodes, data node A, data node C, and data node F, because the replication factor was set to 3. If our replication factor was instead 4 or 5, we would see 4 or 5 nodes in this pipeline. But essentially, the name node is telling the client, you can go ahead and write this block to these nodes in this order. The client then reaches directly out to the data node first in the pipeline, in this case A, and it copies that block of data into that data node's local disk. That data node then reaches out to data node C and sends a copy of that block to data node C's local disk. Data node C reaches out to F, and it sends a copy of that same block to be written to data node F directory. It should be noted that all the communications from A to C to F probably happen on the cluster's much faster network. Between the client and the cluster itself, we probably have a much slower network, and this is why the block copy only happens directly from the client to the first node in the pipeline. We then send a reverse acknowledgement. F tells C, hey, I was able to copy the block. C tells A that, hey, C was able to copy the block, and then A tells the client, hey, we were able to copy the block everywhere. The client then tells the name node, hey, block 000 is in there, and it's written in these locations. Then it requests the pipeline for block 001, the next in the list. The name node updates its memory and its disk representation of the file. It now says that 2013 Apache logs.txt is at this directory inside of HDFS, and it's stored on these slave nodes. It says that this file is now 1 block long. And then we repeat the steps 3 through 9 for block 002 and 003 until we get 3 times replication for every single block that makes up Apache logs.txt. Once all of this happens, we do a final close of the file in the name node. After all the blocks have been written, we can no longer change the file. We say that the file is now immutable. We also have a mapping in the name node's memory space and in the name node's disk. It says that this file, 2013 Apache logs.txt, is now 4 blocks long, a total of 500 megabyte size, and it now has a record of each of these blocks being stored on a combination of these nodes. It should be noted there is no priority node on the data storage. For block 000, A, C, and F are all equal peers. They each store an exact replica of that block, and there is no priority. But did you catch one important thing here? When we were going through that example, I said on the first block write of 000, the name node updates its memory and its disk representation of the file. It says that this file is 1 block long. This is something to be careful of. As you're writing data into HDFS, the name node is constantly updating the size of this file. It will start out saying that the file is 1 block long, 2 blocks long, all the way until it is however many blocks long it is. This is something you need to be especially careful of. Let's walk a little bit through fault tolerance. Let's say that the first data node in that pipeline is bad. Here at step 3, when the name node sends a write pipeline, the client reaches out to A. But let's say A is having a hardware failure or its network has gone bad. A isn't there. The client will now tear down the original pipeline. It'll remove A from the pipeline and try to write to the remaining 2 nodes. This happens the same as if C or F were bad. It would just remove that node from the pipeline and try to rewrite a new pipeline. As long as we get at least one successful block write into the cluster, we know that HDFS via the name node and the data node daemons will take that into account and will ensure the replication factor later. If all of the data nodes are bad, let's say all of them went offline, the client will then reach out to the name node for a new pipeline. If we walk through a little bit more detail, we also know that the client writes checksums on every block write. So for example, when we wrote block 000 into data node A, we also write a checksum of what that block looked like, and we do a validation of that checksum on every read. Data never ever flows through the name node. The block transfers themselves always happen directly between the client and a data node or the data node to the data node. This frees the name node up for doing that orchestration and delegation. The file again is exposed as X number of blocks as each block is written. For this purpose, it's highly recommended that in HDFS you use a /incoming directory and a /ready to process directory. Again, you can choose whatever name you want, but essentially make sure that your upload operations only happen in this directory. Once a file is completely uploaded, you can then, through an HDFS move command, move it into this directory and tell the clients only to read and process data from this directory. Anyone can also be a client, even other data nodes. We'll see when we get to the MapReduce chapter that reducers actually request an HDFS write back into HDFS. This means that individual slave nodes can act as a client of the system. The cluster also needs to have at least as many nodes as you have replication factor. In this case, because we only have 6 nodes, if we set our replication factor to 7 on the client, we would get an error when we try to write the file. The block size and the replication factor again come from the config. If at all possible, we should have that config on the client. As we'll see in other chapters, the client and every node in the cluster have their own configs. Hadoop has defaults for everything. In this case, 64 megabytes for the block size and 3 for the replication factor. Shining a little bit more detail on all this, we recognize that the name node is a single point of failure. Without it, again, there's no file. There's just a bunch of blocks. It's also important to reiterate that HDFS is a virtual file system. The directories that we store aren't actual directories on the data node or on the name node's disk. In HDFS, these directories are represented by an object inside of the name node's memory. That's the only place that these directories exist. The blocks themselves we know exist on the slave nodes, but representing those blocks as a coherent file is the name node's job, and it maintains a virtual mapping of which blocks make up which file. The writes happen in serial. We first write block 000, then 001, then 002, then so on. There is talk of changing this in the next version of Hadoop, but we're stuck with it for the moment. Again, all but that first block write into the first data node all use the cluster's internal network, which is hopefully faster than our client to data node connection. All traffic is optimized. The name node only does metadata operation. The data nodes perform all file data operations, and all blocks except the last are the exact same size. This is important when we get to the MapReduce chapter. Just remember that for the moment. Think of reads as writes in reverse. The client contacts the name node, this time with the get operation, to a specific path in HDFS. Again, this path right here, path in HDFS, exists only in the name node's memory. It is no specific directory on the name node or the data nodes themselves. The name node again sends back a read pipeline for each block. The reads also happen in serial. The reads also happen from the closest machine first. For example, let's say the client was actually node C, and it was reading this file back out to get it on its local disk. If one of the blocks of Apache logs.txt existed on C, the operation making that read would read it from C's node first. This is also the case if C, A, and E, for example, live in one rack, and B, D, and F exist in another rack. When C goes to make the read this time, it would instead maybe read it from A if that was where it existed rather than C. The client reads the block from the first data node to respond. Again, the pipeline is closest first, and then the client requests the next block in the read pipeline. Once the client has assembled all the blocks of the file, it reassembles the file and closes the file. Hopefully this chapter shed a whole lot of light on how a file write happens. We did a step-by-step write operation involving the interactions with the name node and the data node. We talked a little bit about the block checksums, how replication factors ensured, and how fail-safes are handled.